Hello everyone, welcome to today's class. This is Teacher Simon taking you through AS Chemistry Paper 9701-22 for May-June 2025, and this is part 1 for questions 1, 2, 3. Question number 1, part A. Diamond and graphite are both crystalline solids made from carbon atoms. Graphite conducts electricity, diamond does not conduct electricity. And then they are saying this is Roman 1, name the type of lattice structure present in crystalline solids, diamond and graphite. So here we see these ones are having giant structures, okay? This one would therefore be giant. But since they are made of carbon atoms, which are non-metals, then we shall put on molecular, okay? Because we can also have giant ionic. For example, if it is sodium chloride, that is giant ionic. Now, for this case, we are having giant molecular, okay? All right, then next, explain how graphite conducts electricity. Of course, it has free moving delocalized what? Electrons. Free, or we can say delocalized electrons are free to move. That is it. Remember, conduction of electricity can be due to the free movement of electrons or the free movement of ions. That is for ionic structures like sodium chloride. Okay. Then Roman 2, explain why diamond does not conduct electricity. Diamond has no delocalized electrons to move. Delocalized electrons. Okay, it has no delocalized electrons free to what? To move. As simple as that. Part B, separate samples of phosphorus 5 chloride and silicon 4 chloride are each added to an excess of cold water. Then they're saying here, Roman 1, write an equation for each reaction. So, of course, for phosphorus pentachloride, we have PCl5. Then it reacts with water. This is what we call this is a hydrolysis reaction. So here we are going to get phosphoric acid, H3, then PO4, and then plus. What are we going to get here next? It is going to be HCl here. Then we are going to balance. So since these are 5 chlorines, then I'm going to put 5 here. And then what else do we have? What oxygen here has gotten 4. So here oxygen must be having 4. You see that? And then hydrogen will be the 5, then plus the 3. That one becomes 8. So 4 times 2, that is 8. Already phosphorus is 1. And also here it is 1. So that is our answer there. And then the next one is silicon 4 chloride. Silicon 4 chloride is actually liquid. Okay, this one can be a solid, then liquid here, and then here we can have aqueous, and then also here aqueous. Now, when this one reacts with water, what do we get? We get an insoluble solid called silicon 4 oxide. Okay, so it is a solid, then plus HCl here also. Okay, HCl, and by the way, this one is a gas. These are white fumes that are going to come off, so I'm not going to put aqueous, I'll put gaseous. Okay, and also here. Then what else do we have? What else do we have in here? We are going to have this one balanced, so I'll put a 4 here to have 4 chlorines and also 4 chlorines here. Then I'll put a 2 here such that hydrogens become 4, and also here hydrogens are 4, then oxygens are 2, and also here oxygens are 2. So that is it. But since they told us, by the way, to write the equation for the reaction, there is no need to put these state symbols, okay? Yeah, because if you put wrong state symbols, then you get it wrong. So we can just write them without the state symbols, okay? Then Roman 2, they are saying describe the appearance of phosphorus 5 chloride and silicon 4 chloride at room temperature. Okay, this one is a liquid. Okay, this one is a colorless liquid, and this one is, I can say, a white solid, or you can even say, instead of white, you can say also yellow. It's yellowish there, yellowish white solid, but just write one, whether white or yellow. Okay, then next, Roman 3, compare the appearance of the mixtures produced when each reaction is complete. When each reaction is complete, here we are seeing a solid. You see this one here? So there is going to be a white suspension, just like you see porridge. For porridge, if you get, let's say, maize flour and then you mix it in water, what you get is a suspension, because this one is not soluble. Okay, something like that. So we are going to see a suspension. Okay, and then here we are getting a clear solution, because this one is an acid, mineral acid, which is soluble. So this is a clear solution, but here there is a white one, suspension. Okay, so I can say phosphorus pentachloride, phosphorus pentachloride produces a colorless solution. Then silicon 4 chloride produces a white precipitate, okay, a white suspension. Silicon 4 chloride produces a white precipitate. As simple as that. Then part C, some oxides are amphoteric. Describe what is meant by amphoteric. That means this compound can behave as an acid or as a base, or it can react with both acids and bases. So I will say ability to behave as both an acid and a base. Or you can say it can react with both acids and bases. As simple as that. Then Roman 2, identify one formula of period 3 oxide that is amphoteric. That is aluminium oxide. So we shall have aluminium, then oxide. Remember, they say the formula. So if you write aluminium oxide, you might be crossed. Okay, so they said formula, you write the formula, aluminium oxide. Another oxide that is actually amphoteric, but it is not coming from period 3. So the element is actually zinc. So we have zinc oxide. This one is also amphoteric. Part D, the melting points of different oxides are shown in this table. Roman 1, they are saying complete this table by identifying the strongest force of attraction in each oxide that is broken during melting. Use the abbreviations below. Now in melting, remember, we are moving from the solid, from the solid to the liquid. So that means we are breaking the intermolecular forces of attraction, the forces in between molecules. You get it? So the molecules have been, let's say, together there, and then we break them up. If, let's say, it is water, you break the molecules so that they are moving like that, and they are in liquids. But in the solid, they were closely packed. You get that? So we have to keep that in mind. Now, they said the strongest force of attraction. That means they might be more than one, but which one is the strongest? When you look at this sulfur dioxide, you are having sulfur here and then oxygens. So if there are two, I can say those are two. Then sulfur has how many electrons in the outermost? Sulfur has 6. So it shares with the oxygen here. So we can have a double bond here. Remember, oxygen also needs 2. So oxygen shares 2 electrons here and also shares 2 electrons here. You get it? Now, sulfur has how many electrons shared? This is 1, then 2, then 3, then 4. That means we are having 2 that are remaining. So it will form a lone pair here. Now, there is going to be that lone pair of electrons here. Now, since these are 2 oxygens, we would expect sulfur to be linear. This sulfur dioxide, the shape to be linear, but it is not going to be linear because using valence shell electron pair repulsion theory, okay, we are going to have the repulsion between the lone pair here and the bond pair being stronger than the bond pair. So because this one here, the repulsion here and also here is bigger than the one in here, so it is not going to be linear, but instead it is going to be what? It is going to be non-linear, okay? Non-linear. Now, what we are going to have, you know that oxygen is more electronegative compared to sulfur. So this one is going to be partially negative and this one partially negative because it tends to pull the bonding electrons towards itself, the oxygen. You get it? This one is going to be partially what? Positive. Now, since these ones are pulling down, the oxygens are pulling down as sulfur is less electronegative compared to oxygen. Now we are going to see the overall dipole, okay? The overall dipole moment moving downwards like that. You see that? Okay, so now this one is going to be a polar molecule. So the force of attraction during the melting, because this one is polar, then there is going to be attraction to others, okay? So there is going to be that permanent dipole. You see that? So here I'll just put PD. Okay. Then next, when we go to water, just like this one here, oxygen has 6 electrons in the outermost. This is 1, 2, 3, 4. Then there is 5, then 6. You see that? So since the repulsion, again, we are using VSEPR, valence shell electron pair repulsion theory. Okay, we are using that. So since the repulsion between these two lone pairs is stronger than the repulsion between the lone pairs and the bond pairs, and in turn also that one is stronger than the bond pairs, we are going to have what we call a V shape. Okay, so the angle that is actually here is bigger than the angle that is here. Why? Because here we are having two lone pairs compared to this one, which is just one lone pair. You see that? Now, in here, oxygen is more electronegative compared to the hydrogens. So hydrogens are partially positive. You see that? So even here, we are going to have, this one is PD. So there is PD permanent dipoles. They are there. But we also have hydrogen bonding elements that have hydrogen bonding. Let me even write it here. Elements that undergo hydrogen bonding are, we have fluorine, we have nitrogen, and oxygen. So if these elements in there are connected to a hydrogen, they will always form hydrogen bonding. You get it? So this one here will have hydrogen bonding. So this one will connect to another one, let's say the oxygen, which is already partially negative, right? Like that. So they continue like that. Partially positive connects with the partially negative. So there is going to be hydrogen one bonding in here. And hydrogen bonding is stronger than the permanent dipoles. So here I'll put hydrogen bonding. Okay. Then next, we also have silicon 4 oxide. Silicon 4 oxide its structure is like that of diamond. Okay, so let me show you what we have here. Now this is the book that I use, this old edition here. But if we check in chapter 5, states of matter, okay, and we look at the structures here, a lot of things in here. When we talk about the forces, the intermolecular forces here, you look at the one of graphite, there are those layers there, okay? Then there are these free electrons that are free to move, so making graphite able to conduct what? Electricity. And then when we go to silicon 4 oxide, and diamond. You see, this is the one here. For diamond, we are seeing carbon atoms. A carbon atom is surrounded by 4, so it forms that tetrahedral structure. Okay, strong covalent bonds. And then when we come to this one here, they say that each silicon atom is bonded to 4 oxygen atoms, but each oxygen atom is bonded to only 2 silicon atoms. So the formula for silicon 4 oxide is SiO2. So silicon dioxide has properties similar to that of diamonds. Okay, so it is very what? It is very hard. You see that? That's why it is even insoluble in water. Okay. So this one here, we can see that if you can look at that structure, it is just like this one. We are seeing the tetrahedral structure. Now coming back to this one here, we are having only covalent bonds. Okay, this one is not going to have, it's not going to have intermolecular forces of attraction. Actually, silicon here, what I mean, it is not going to have these permanent dipoles. Silicon is a metalloid. It has properties of nonmetals and then properties of metals. Okay, so this one is going to be just covalent. Very strong covalent what? Bonds. They are the ones you break. So because they are strong, you can see the melting point is high. Then of course, the melting point for silicon 4 chloride, I mean sulfur dioxide, is very low. That means this one is a gas, simple molecular structure. Even water, simple molecular what? Structure. Then when we go to Roman 2, oh no, sodium oxide. This one has gotten sodium ions, okay, and then the oxide ions. So these ones are 2 of them, such that they balance these 2 minus. That's why you're having this. So this is ionic. That's an ionic bond. And of course, if you are melting this one, you are going to break these ones completely, such that sodium ions are detached from the iodide ions. I mean from the oxide ions, sorry. Then next, magnesium oxide, even this one, we are seeing ionic. Okay, ionic bond, as simple as that. Then Roman 2 here, they are saying that a student suggests the following hypothesis. The stronger the covalent bond between atoms in nonmetals, the higher the melting point. The stronger the covalent bond between atoms in nonmetals, the higher the melting point. First of all, we look at melting point. For melting point, we have 2 factors that we look at. We look at 2 things. Number 1, the structure and bonding. Then number 2, we look at the strength of the bonds. Okay, if it is hydrogen bonding is stronger than the PDPD, things of the sort. Ionic bonds are stronger than the covalent bonds, or are stronger than the van der Waals forces of attraction, things of the sort. Metallic bonds are stronger than, if of course you have, let's say, sodium oxide, and then you also have sodium as a metal. So metallic bonds are stronger than the ionic bonds. So things of the sort. Okay. Now here they are saying that the stronger the covalent bond between the atoms, the higher the melting point, based on what we are having in here. So this person is trying to put up a hypothesis, and they're saying that use this table to deduce if this hypothesis is true or false, or if there is not enough information to make a conclusion, and then you explain your answer. Now, we are going to look at what we are having up here. When you check here, if this person says that the covalent bond between atoms in nonmetals, the stronger the covalent bond between atoms in nonmetals, the higher the melting point. Now, where do we have the nonmetal oxides? The nonmetal oxides, we are seeing this one here. We are also seeing this one here. But the forces that are being broken down are hydrogen bonding. Do you see this one? Hydrogen bonding. And then in here, yes, we are having the intermolecular forces of attraction. Here there is also intermolecular forces of attraction, but the strongest are these ones, the hydrogen bonds. You see that? So we don't actually break the covalent bonds between these atoms. Those are not the ones that we break. You see that? But for silicon, for oxide, we are breaking the what? The covalent bonds. So for that case, I would say that there is not enough what? Information. Not enough information. Why? Because one satisfies. We can see this one satisfying. There are strong covalent bonds and then there is higher melting point. So I would say not enough information. They would have given us very many more. Not enough information. And then my reasoning will be sulfur dioxide and maybe water, okay, do not break covalent bonds. Don't break covalent bonds when they are melting. You see it, just the intermolecular forces of attraction in between the molecules. Okay, it's only silicon 4 oxide that breaks the covalent what? Bonds. You see that? It is only this one that breaks. And then we move over. Of course, we are not going to talk about what? These ones here, because they are ionic and the oxides are coming from metals. Okay? And the reference was on non-metal oxides. Question 2. A sample of iron contains 3 different isotopes and has a relative atomic mass of 55.8. And they're saying Roman 1, part A, define relative atomic mass. So this is because the relative atomic mass, we get it. Remember, when we are calculating, we say summation of isotopic mass, then times the relative abundance. So that means we are using isotopes, the masses of isotopes. So this is the average, weighted mass of naturally occurring isotopes of an element on a scale that the mass of one carbon 12 atom has exactly 12 grams. Or you can say unified atomic mass unit, okay? And that is that. This one here takes actually 1 mark, and also this other one here takes 1 mark. So those are the 2 marks. Then Roman 2, this table here shows the abundances of 2 isotopes present in the sample of iron. We are given the masses and then the abundances. And then they want us to calculate the relative isotopic mass of the 3rd isotope. Okay, remember AR is equal to the sum of isotopic mass, then times the relative what? Abundancy, times, I can say just abundance, percentage abundance actually, abundance. So that means I'm going to have AR is what? 55.8, not so? 55.8. It was given here, you can check, 55.8. And then, which ones do we have? So here we have 53.9, then times, the percentage abundance is 6, out of 100, then plus, this is 55.9, 55.9, then times the percentage is 91.9 out of 100, then plus, the other one is going to be, we don't know, okay? But the percentage abundance is going to be what? When we get these two and we subtract them from 100, first of all, this one is going to be 97.9. So what is remaining here? A 1, then this one has to be a 2, and then a 0 here. So when we add, we get a 10 here, then take 1 here. That will be a 10, then take 1 here. So we have 100 there. So that means it is 2.1, okay? So I will have here plus 2.1, or that other one, I don't know it, okay? Let it be x. Then now times, that is the mass of the third isotope, okay? Then times, this is 2.1 out of 100. You see that? Now, I can have these ones here subtracted from this, okay? 55.8, then subtract these two here. 53.9, then times 6 out of 100. Then we shall also add 55.9 times 91.9 out of 100. Then this all together gives us that, okay? So that is 54.6061, which is equal to 2.1 out of 100 times x. So meaning your x is going to be, when we cross multiply, then we divide all through by what? 2.1. So it will be 55.8 minus 54.6061, okay? Then we are multiplying it with 100, and we are dividing it by 2.1. So what will be our answer? So the answer I've gotten here, I will say 55.8 minus that answer. We get that, then times 100. We get that, then divide by 2.1. And the answer becomes 56.85. But since all of these ones have been to one decimal place, okay, I'll write 56.9. 56.9. Three significant what? Figures. Then part B, they are saying deduce the number of pairs of electrons in 3D subshell in iron 2. Now, iron 2, iron, that means it has lost 2 electrons in its outermost. So first of all, we are seeing iron is in position 26, right? So if it is in position 26, then the electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. This is the argon, okay? That's the argon electronic configuration. Now, how many are remaining? We are having 26. Are we there? Then minus 18. 18, because these are 18 electrons there. We shall get 8. Not so. Then after getting 8, those 8 are going to go into 4s and then the 3d. Remember, 4s is filled first before the 3d because of that overlap. Now, that means we shall put 2 here, and then the 6 will go here, such that this is a total of what? Of 8. And then when this one is losing electrons, it loses first from the 4s, okay? So that means we shall have 0 electrons in the 4s, and then 3d6. You see that? So we are going to have this one here. This is for iron. Then for iron 2, we are going to have 4s0, 3d what? 6, okay? And then the rest, all of these ones are the same. So just duplicate and then put there. This is for iron 2. Position 26, even this one, position 26. It is electrons that have been lost, but not protons, okay? Okay, so now they are saying deduce the number of pairs of electrons in the 3D subshell. So this one here, the 3D, which has 6 electrons, using the Paul's exclusion principle and Hans rule, we are supposed to first assign 1 electron, okay, Paul's exclusion principle, 1 before we pair. And then the Hans rule, we do opposite spins. So you put like this. If you are coming back, it has to be like that. But don't put them all spinning in the same direction, because these ones are having the same charge, so they repel each other. So the next one, we put it when it is facing down like that, okay? But those are 5. Here we need 6 of them, so it will come to this one here, and this is 1 pair. Number of pairs of electrons in the 3D, it is only 1, okay? So we shall write this one as 1 pair, as simple as that. Part C, sketch the shape of the lowest energy orbital in the shell with principal quantum number 2. So principal quantum number 2, we are looking at 2s2. We have 2s2 and 2p6, okay? Those are the ones which have the number 2, okay? Then the ones that have 3, we have 3s, 3s, 3p, and then the 3d. That is principal quantum number what? Principal quantum number 3. Now here for quantum number 2, the one with the lowest energy orbital is the s orbital, and the s orbital is spherical. So we shall draw this one spherical. S orbital is spherical. So that is the one you draw. If it were p, then we would draw lobular, okay? For p, they are like lobes there. You get it? So that is that. Part D, complete this table to show the information about particles in one ion of iron 3. Of course, when we check back here, we have seen that for iron 2, we are having how many electrons here? There are 6 in the 3D. So that means if it loses another electron, now it is going to come from the 3D, because the 2 have been removed from the 4s electron. So that means here we won't have another electron. So we shall have only 1 here, 1 here, 1 here, 1 here, and 1 there. You see that? So now, when we go back to this one here, electrons, first of all, how many were they? You can check here. These ones are 18. 18 plus 6. Okay, 24, not so? Then 24, or you just say this is 26, then minus the 3 electrons that we have taken away from here. Remember, for any atom, the number of protons is equal to the number of electrons. Are we there? Then for the ions, if it is positively charged, that means those are the number of electrons that have been removed. So if we have iron 3, that means we have removed the 3 electrons, and we are remaining with 3 protons in the nucleus who don't have the counter electrons in the orbit or in the shells to cancel out their what? Charge. So that's why it remains with a plus. Okay, so that simply implies that we are going to have 26 minus 3, that is going to be 23, not so? So we shall have here 23. Then here they are saying that the number of particles in there, if they are 30. Now let's look at iron. Iron 56. Then of course this is 26 here. So if we get 56, then minus 26, this one gives us 30. Which number is here? And we know that this is the mass number. Okay, this one here corresponds to protons plus what? Neutrons. You see that? And this one here corresponds to what? Protons. You see that? So this simply implies that what we get here after subtracting is going to be the what? The neutrons. So here we shall write neutrons. As simple as that. Then next, we have the atomic radius of iron is this one here, 1.26 times 10 to the power of negative 10 meters, suggests the change in the radius, if any, after an iron atom reacts to produce iron 3. Now, first of all, we see when you check back here, one shell has gone. This is for iron 2. Then one electron has gone from here, so we are having a 5. So one shell has gone. So because one shell has gone, then we are going to see a smaller iron. And also now the nuclear attraction for the outermost shell electrons is going to increase. You see that? Because one shell has gone, and therefore the shielding has reduced. So since shielding has reduced, the nuclear attraction for the outermost electrons becomes bigger. So we shall suggest the change in the radius. The radius decreases. This is because an electron shell has been lost. This reduces the shielding effect. This reduces the shielding effect. Therefore, increasing the nuclear attraction. The nuclear attraction for the outermost electrons. So in that case, as it pulls those electrons towards itself, the nucleus, okay, then the radius has to decrease. So we are looking for the radius decreases, and these are 2 marks. Why? Electrons have been lost. Even if you stop here, it is okay. But it is always important to talk about the nuclear attraction, because it is the one that brings out that effect properly. Question 3, part A. This one is propene reacts with HBr, hydrogen bromide, in an addition reaction. In Roman 1, they are saying define an addition reaction. This is where 2 or more reactants react to form only one product. So they fuse into each other to give you one, okay? This is when 2 or more reactants react to produce only one product. Simple as that. Then Roman 2, complete this figure to show the mechanism for the addition reaction between propene and hydrogen bromide to produce 2-bromopropane. Include charges, dipoles, lone pairs of electrons, and carry arrows as appropriate. Okay, now, since hydrogen bromide contains 2 elements with different electronegativities, bromine is more electronegative compared to hydrogen, okay? So it is going to attract bonding electrons towards itself, thereby attaining what we call a partial negative charge, because receiving of electrons is you become negatively charged, right? Then this one becomes partially what? Positively charged. And as this one draws closer to this electron density here in this pi system, this one has gotten electrons. So the pi density here is intense. So that means that we are going to have this one is negatively charged. So it will be attracted to the what? To the positively charged. Now this hydrogen in HBr appears to have lost electrons, okay? Then this one offers those electrons. It donates the electrons to the hydrogen what? The hydrogen atom in here. And then from there, we can have our carbon here. Then this is the CH3 here, then a hydrogen. Okay, now we always say that the rich get richer. the carbon with more hydrogens gets the hydrogen first. So we shall have now a carbon here, and then we have the 3 hydrogens. Then this one will have a positive charge. So this one is a carbocation. You see that? Then, of course, when they gave electrons to this one, then this one had to break off. You see that? That one had to break off. And then when it breaks off, then we are going to have bromide ion coming off. Now the bromide ion that came off from here, it now became bromide ion, not even just partially negative, okay? Because it has now finally received all the electrons. Then it will donate these electrons here. There is a lone pair. It will be donated to this one here, which appears to have lost electrons. And then from there, we have this CH3, which is here. Then this carbon, okay, has this CH3, which is here. Then there is this Br we have gotten here, and then there is the hydrogen. You see that? There is also another product you can get, whereby you will have this CH3 here, okay? Then there is this carbon here, and then it receives the what? The carbon, the hydrogen first. And then here we are getting the CH2, then we have this. You see? Now, this one, I can actually write it as CH3, CH2, okay? I can write it as CH3, then CH2, then CH2, now plus. Now this bromine can come here and donate to this one, then we shall have CH3, CH2, CH2, Br, okay? This is one bromopropane. Okay, but here we are seeing one carbocation. I mean this carbocation here. There is one alkyl group here. Okay, so the positive inactive effect that comes from this one alkyl group is not so strong compared to this one here that has gotten from 2. So there is this CH3 here, which it is donating the electrons. There is also this CH3 here. So these are 2 alkyl groups. So there is stronger positive inactive effect. So where there is stronger positive inactive effect, then that becomes the major product that comes out of there. Okay, so the major one is this one we have gotten here, okay, but not this one. Okay, so that is that is what we are supposed to have there. Then they are saying, it is Roman 3 actually. Explain why the major product of this reaction is 2 bromopropane rather than 1 bromopropane. So we can say that 2 bromopropane comes from a secondary carbocation, which is more stable, than the primary carbocation. Full stop. Then you have to talk about the other mark has to come from the strength. Stronger, we see stronger positive inductive effect in secondary carbocation. Okay, in this with two alkyl what? Groups. One alkyl group is here, another one is here. Okay, So that is that stronger positive inductive effect. Now, here I said before, there's something I said that the rich get richer. This one is rich in hydrogen, so it will get the hydrogen first. Now, you also come here and you say when you are explaining that the rich get richer. My friend, that's not a chemical answer, okay? It's not an answer in chemistry. Part B, hydrogen and nickel are added to alkene X. That is what we call hydrogenation. Nickel is acting as a catalyst, okay? This figure shows how the concentration of X changes, that is the alkene, changes with time. We can see, yes, it is decreasing. It has to decrease, the concentration has to decrease because these ones are reacting. The carbon to carbon double bonds are being depleted. They become carbon to carbon single bonds, okay? Because a hydrogen comes and then a hydrogen comes here, and then they take away the double bond, okay? So the concentration of this one has to reduce. The concentration of reactants has to be reducing, and then the concentration of products has to be increasing. But as it is decreasing, we see that somewhere from, let's say, 400 to 600, it is constant. So that means what is being added is maybe used up, and we still have some more concentration of what? Of this X here, the alkene. You get it? So this simply implies that the alkene, I mean the hydrogen, the supply of hydrogen is now the limiting reagent. Okay. Now, Roman 1, they are saying use this figure to identify the limiting reagent in this reaction. This has to be hydrogen. Okay, hydrogen gas. Why? At the end of the reaction, we can say there is some concentration. There is some concentration of X at the end of the reaction. Like I said here. Okay, then Roman 2, they're saying use figure 3.2 to describe how the gradient changes as the reaction proceeds. Of course, the gradient, it is decreasing. At first here, it is very steep. But as you go on like this, when you are drawing lines, if a line is like this, that means in here, you are seeing for a very short decrease, I mean increase in the X here, you are seeing a drastic decrease in the Y. You see that? So a big change in Y divided by a small change in X, you are getting a big change, okay? But again, if you have a line that is like this, okay, that means for a big change in X, this is a big change in Y. So a small change in Y divided by a big change in X, you are going to get a very smaller change. So that means the rate of reaction keeps on decreasing as the reaction goes forward. You get it? As the concentration of the reactants keep on decreasing. If the concentration of the reactants keep on decreasing, then the reaction is going to slow down. You get that? So we shall say that they say describe how the gradient changes. First of all, it is decreasing as the reaction proceeds. State what this shows about the rate during this reaction. Okay, we shall say that the gradient reduces. The gradient reduces, therefore, the rate of reaction decreases. As simple as that. Part C, hydrocarbon Y contains carbon-to-carbon double bonds. Okay, there are two of them. There are no other functional groups present. Carbon Y reacts with excess of hydrogen gas to produce hexane. Okay, to produce hexane. Then they are saying use this table to calculate the enthalpy change per mole of this hexane produced in this reaction. Now I can have, let's say this is 1, 2, 3, 4, 5, 6. Okay. And there are two double bonds. Maybe I can put this one here and maybe this one here. Okay. And then I can have, I'm just assuming, so this is CH3. Of course, this one has to be 1H because these are 2, then 3, then 4. You see that? Then here we shall have also a hydrogen. Then here a hydrogen, and then this one has to be 3 of them. Now, if we can count, these are 3, 6, and then 10. Okay. Then plus, we are having hydrogen, and then what we are getting is this one here. So it is, I can just draw this one here. And then I'm going to take away the double bonds. So I'll take away double bond, then put a hydrogen. Wherever there was a double bond, so I had something like that, okay? Then wherever there is a double bond, I have to put a what? A hydrogen. It's a molecule. So here, and then here. Again here, and then here. For this one to become saturated, right? And then here, we are having how many carbon to carbon double bonds do we see here? This is 1 and this is 2. Okay, so we are seeing 2 carbon to carbon double bonds. Are we there? Then we are seeing carbon to hydrogen single bonds. What do we see? Or even carbon. Let's first finish carbon to carbon single bonds. How many do we see? There is, this one is 1. There is 1 here, then 2, 3. Not so? Those are 3. Carbon to carbon single bonds. Then we also have carbon to hydrogen single bonds. So carbon to hydrogen, what do we see? These ones are 3 because there is 1, 2, 3. Okay, so those are 3. Then 4, 5, 6, 7, 8, 9, and 10. See that? Those are 10. 10. Anything else that is left here? I think nothing. Then, of course, each molecule of hydrogen, one goes here and then another one goes here, the atoms. So if these ones are 2, that means there is another molecule here. So they have to be 2 molecules. So I'll balance this by putting 2 molecules here of hydrogen. So we have hydrogen, then there is also another hydrogen. You see that? Then when we come to this one here, we are seeing only carbon to carbon single bonds. Okay, how many are they? Do we see carbon to carbon? This is 1, 2, 3, 4, 5. You see that? So those are 5. And then carbon to hydrogen. Remember, we don't have carbon to carbon double bonds. They are depleted by adding what? Hydrogen. And then these ones are going to be 3, 5, 7, 9, 11, then 14. You see that? 14. Now, when we are finding the enthalpy change, it is going to be energy in breaking. Okay. I can actually say H breaking, then minus the H forming. So the energy for breaking, you are breaking these bonds and then you are forming these. So energy breaking, bond breaking is endothermic because you are putting in energy to break. You get that? And then bond formation is exothermic. So here we shall have, this is the enthalpy change that goes in here to form this. So we are going to have energy for breaking. We have 2. Let me just put this one here. 2, then times carbon to carbon double bonds, we are seeing 610. Then we are seeing 3 carbon to carbon single bonds. Carbon to carbon single bonds, 350. Then we also have 10 carbon to carbon hydrogens. 410, which is here. Then after that, we shall now add on. We come to this one. Hydrogen to hydrogen is 436, and there are 2 of them. So 2 into 436, like that. Then we subtract. Now, we come to this one here. Here we are seeing 5 carbon to carbon. So I'll have 5, then times. But carbon to carbon here, we can see the bond energy is what? 350. So I'll put 350 here. Then plus 14 carbon to hydrogen, 14. Carbon to hydrogen is 410. Okay. Then what is the total energy for breaking the bonds here? 2 into 610. Then plus 3 into 350. Then plus, of course, 10 times 410, that will be 4100. Then plus 2 into 436. Then altogether we get 7242. Minus, then what is the total energy for formation of the bonds? 5 into 350. Then plus 14 into 410. This one gives us 7490. Okay, so since the energy for formation of the bonds is bigger than this one for breaking the bonds, that means the total energy change here is going to be a negative, okay? And that means the process or the reaction is exothermic. The forward reaction is going to be exothermic, or if it is an equilibrium. And then if the energy for breaking is bigger than the one for formation of bonds, that means the whole process is going to be what? Endothermic. So what is the difference here? 7242 minus 7490. We get negative 248. So that is negative 248. That is that. Part D, hydrocarbon Y reacts with hydrogen. Then figure 3.3 shows the distribution of energies of hydrogen at temperature T. Area A represents the number of molecules with energy greater or equal to the activation energy. And remember, activation energy is that minimum energy required for particles to have, okay, for them to do what? To react. Minimum amount of energy particles must have in order to react. And then part Roman 1 here, they are saying annotate. That means to write, just like I've been writing, okay? We draw something on that shape to show the effect of adding nickel. So if you add nickel, first of all, this one is a what? Is a catalyst in this reaction. So a catalyst provides a pathway with the lower activation energy. You see it? So if it provides a pathway with lower activation energy, then we are going to have these particles which were having little energy, okay? Little energy to react. Their energy was not bigger than the activation energy, so they are going to be in position to react. You see that? So here I will put EA. Of course, we are saying this one is going to be smaller. It is providing a pathway with lower activation energy. So we have to put it on the what? On the left of this one here. You see that? And then the particles now here, you are seeing that now you are having very many which can be in position to react. You see that? Then from there, they are saying that area B, not labeled on that figure, represents the number of molecules with energy greater than or equal to the activation energy when nickel is added. You see? Now, this is the activation energy they must have when nickel is added. So, this is area B actually. Area B. This is the one that I've shaded. The whole of this here, including the one of A. So, you can see that the region B is bigger than that of what? Than that of A. You see that? And then they are saying that state the difference, if any, between the areas A and B. The difference is there. Okay. Area B is bigger. We can say greater, whatever, is bigger than area A. Explain the significance of your answer on the rate of hydrogenation of Y. Give the answer in terms of what? Collision. Now, if you're having these particles which have energy greater or equal to the activation energy, you are going to have, first of all, we are going to have more molecules. You can see the area is bigger. More molecules have energy greater or equal to activation what? Energy. So because of that, we are going to see greater or increased number, increase in the number or in the frequency, increase in the frequency of successful what? Successful collisions. Because many have gotten the energy to react, so the collisions are going to be successful. As simple as that. Then this one here will increase the rate of the reaction. You see that? Increasing the rate of hydrogenation of Y. As simple as that. So tell us about this region being bigger. So there are 4 molecules with energy bigger than activation energy will have more frequent what? Collisions. As simple as that. Then part E, they are saying that alkene Z contains 2 carbon-to-carbon double bonds. Z reacts with an excess of hot concentrated potassium permanganate to produce only, this is a ketone, propanone, then we have a dicarboxylic acid here, and then we have carbon dioxide and then water. Suggest the structure of Z. First of all, we are going to have something here. So let me begin with this one. CH2, COO. Now, because there is COOH here, okay, we are going to have this one here, then the OH, then here we are having carbon dioxide, okay, then there's also C here, then OH here, and then here I'm going to have C, then this, in fact, make it much more clear, I'm going to put this one here, then CH3, and then CH3. So this is what happens. You have a carbon, a double bond, and then a carbon. So with hot concentrated acidified potassium permanganate, we are going to see this double bond broken and then we oxidize. Okay? Now, if I take you through this book here, see what happens. If we check hydrocarbons, that is chapter 15 here. Hydrocarbons. We see oxidation of alkenes. It has to be an oxidation of alkenes. So slowly, these are alkenes. Of course, if you use cold dilute acidified potassium permanganate, you are going to get a DIO. Okay? If it is cold and dilute. But then if it is hot and concentrated, this is the one here. So if in a double bond you have the 2 carbon atoms, the 2 hydrogens connected on the carbon, you are going to get a carbon dioxide. Actually, what happens is that when we are breaking here, then these ones are oxidized. you are going to first have methanoic acid, but this one is unstable, then it breaks down further to what? To carbon dioxide and then water. So that's why you're seeing that they are giving us what? Water. You see this water here? Now, that is one. Then number two, if you have now one alkyl group and then hydrogen, when you when this one is oxidized, first of all, you are going to form an aldehyde. And then an aldehyde is oxidized further to give us what? A carboxylic what? Acid. You see that? We get a carboxylic acid. Then, if we have only alkyl groups connected to the carbon here, then when we break here and we oxidize this one, we get a ketone. You see that? Now, let's go back to what we are having here. There is this ketone here. So now I'm going to put this double bond and then break this one here such that when I oxidize this one and it gives me a ketone, then I should have the CH3 here and the CH3 here. You see that? So now I'm drawing the structure of Z. So I'll begin with a CH3 here and then also a CH3 here. So when we break, then we are getting this one here. Are we there? Then this carbon atom, because this is a carboxylic acid here, then I must have it having a hydrogen. Okay? It must have a hydrogen because remember, we have checked here that if it has a hydrogen, we are going to get an aldehyde, and then after further oxidation, we get a carboxylic what? Acid. Are you connecting? Now, I will come back to this one here, and I put a hydrogen, then go to this one because after oxidizing this one, then it will give us the carboxylic acid. Then we shall put CH2, then C here, because this one is a carboxylic acid, then there is a double bond here, but it must have a what? A hydrogen here. You see that? Then how many do we have? The bonds, this is 1, this is 2, this is 3, 4. Then I will put a carbon here. Now this one must be having only what? Hydrogens. Why only hydrogens? Because it will be broken down to give us the carbon dioxide, okay, and the water here. You see that? So this is the structure of Z. So this has been it for this first part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next videos.